All right, so I was setting this up last time. So this is problem number 7 in the last video. And let me just read it again. A distant galaxy is receding from Earth with a radial velocity of 3,000 kilometers per second. At what wavelength would its Lyman alpha line be received by a detector above Earth's atmosphere? Of course, it's got to be above Earth's atmosphere because the Lyman alpha line is this 121.6 nanometers. That's what lambda 0 is in the Doppler equation, which this is the Doppler equation, of course. Remember, we're solving for lambda, the moving wavelength. Anyhow, the 121.6 is in the ultraviolet, so that our atmosphere blocks that quite efficiently. As a matter of fact, anyhow, that particular wavelength won't get through the atmosphere. A little bit of ultraviolet light does get through the atmosphere, but not that particular wavelength. Anyhow, so we just take this equation, we solve for lambda, and so that means to bring the lambda naught over the other side of the equation, and it's going to be 1 plus, this is the quantity, 1 plus the velocity, the moving velocity, and they gave us what that was in kilometers per second, divided by the speed of light, which that's what c is. Of course, that has to also be in kilometers per second. All right, so here we're setting it up. Lambda is equal to the Lyman alpha wavelength that you'd observe in the laboratory. That's what lambda naught is, times the quantity 1 plus 3,000 kilometers per second divided by 3 times 10 to the 5th kilometers per second. Of course, the kilometers per second cancel each other, and so that's just going to be a number times the wavelength. And of course, it's a number. Notice it's a number that's greater than 1, which of course also tells us that of course it is red shifted, right? Because the wavelength increases, and it increases to at that particular speed at 3,000 kilometers per second. It will increase to 122.8. So let's write that down. Lambda increases to 122.8 nanometers. All right, so that's from the Doppler shift, right, or the Doppler effect, as it's called. So that particular wavelength goes from, again, because of this speed, the relative speed between the detector and the object that you're looking at, the source. In this case, it's a distant galaxy. So the wavelength is now 122.8 nanometers. All right, let's move on to the last question in this chapter, the last problem in this chapter, problem 8. All right, so here's problem number 8. I've started setting it up. I'm going to read it. It says, in a demonstration of the photoelectric effect, suppose that the minimum energy of 5 times 10 to the minus 19th joules, and they put in parentheses 3.1 electron volts, is required to dislodge an electron from a metal surface. What is the minimum frequency and the longest wavelength of the radiation for which that detector registers a response? In other words, we have to figure out what the frequency is of this photon, and we also, so we don't know that, and when we figure out the frequency, we can certainly figure out what the wavelength is. All right, so in fact, we're going to figure out the wavelength first. All right, so notice in this particular problem, they gave us that it was, in electron volts, it was 3.1. I just did a little conversion here, so it's, they approximated it. Recall that for 1 electron volt is 1.6 times 10 to the minus 19th joules, and notice the times 10 to the minus 19th will actually cancel. I mean, you can put this in your calculator to verify it, that this and this cancel, and so it's really just 5 divided by 1.6, so it becomes 3.125 electron volts. All right, so the basic idea is you shine some light on a piece of metal, right? So here's some photons that come down there's a longer, there's a, longer wavelength photon, and then, there's some, let's say, some really short wavelength photons that come down. And the longer wavelengths, you won't get any photoelectrons, right? So there's zero electrons coming, bouncing. This represents the metal. But with certain wavelength, when you get to smaller and smaller wavelength, remember that means higher and higher energy. Then eventually you'll get if it's this photon right here, you'll get a photoelectron. So an electron will come off the metal, and we can detect that, right? Because of course moving electrons are current, and we can detect the current. All right, so how do we do this? If we know that this is the energy, we can figure out what the wavelength of that photon is, of course. They tell us this in the problem, that it's, they approximated it to 3.1. We're going to use 3.125. Anyhow, the wavelength of the photon will be, of course, remember our constant, 1240, and the units are in nanometers times electron volts. Right, we've used this several times. That's supposed to be an E. So, and then, if we know the energy in electron volts, so we just divide by 3.125 electron volts, and notice the electron volts cancel. So put this number in here and my calculator, and I get, notice the answer will be in nanometers because that's the units that are remaining, would be 396.8 nanometers, right? Which is, that's just barely in the ultraviolet region. Remember, the bluest light the human eye can see is about 400 nanometers. So this is actually really close. All right, so that's the wavelength, and of course to figure out the frequency. Here, I guess I'll probably need a little bit more room here, but anyhow, to figure out the frequency, so this is f, is just going to be the speed of light divided by the wavelength, right? So it's the speed of light divided by the wavelength, and of course the wavelength has to be in meters, but that's easy to change if you know your metric prefix, not nano. Remember, nano, right, means lowercase n means times 10 to the minus ninth. All right, so we're going to leave c in meters, so this would be 3 times 10 to the 8th meters per second, divided by 396.8 times 10 to the minus ninth meters, right? And of course the meters cancel, and that's good because then you get your answer in 1/seconds, which is hertz. That's the same thing as hertz. All right, so again, we found that the wavelength was 396.8 nanometers, but of course we can write that instead of nano, we write times 10 to the minus ninth meters. We put that in the equation, f, the frequency is equal to the speed of light divided by the wavelength, and so I've done that down here. Here, let me use the mouse. So I've done that down here, and so 3 times 10 to the 8th divided by 396.8, which is also, by the way, 3.968 times 10 to the minus 7th. That's the exact same number. The meters cancel, so let's do that. The meters will cancel, and so it leaves us with 1/seconds. And what number does it leave us with? It's 7.56, roughly 7.56 times 10 to the 14th hertz. All right, so that is sometimes that's called the cutoff frequency. So basically, frequencies below that will not, will not generate what are called photoelectrons. And remember, I think I mentioned this before, but Einstein was actually the one that explained the photoelectric effect using the new ideas in quantum mechanics. That photons could be thought of as particles that can certainly contain energy, yeah. All right, so that's the problem. Make sure you know how to do these, not only for the homework, but also for test one. And of course, some of these problems will eventually find their way onto the final exam. I know that's a long way from now, but it's certainly something to think about. All right.